So postulate 3 and 4 actually are answer to those questions, that how really you will be using these operators to get information. Postulate 3, it gives you regarding individual measurement, and postulate 4 gives you something on average measurement, or we call it sometimes expectation value. So now let us quickly see postulate 3 and 4 one by one. First, postulate 3. It tells you that in any single measurement of the observable that corresponds to the operator A cap, the only values that will ever be measured.
স্যার
হ্যাঁ,
কোনো প্রেজেন্টেশন দেখতে পাচ্ছি না।
gives you one of the eigenvalues, right? So what is the eigenvalue? That also you know that it follows A psi equal to A psi. This is the equation. Okay, this is another version of the postulate 3, that in any measurement of the observable associated with the operator A cap, the only values that will ever be observed are the eigenvalues A, which satisfy the eigenvalue equation this. So suppose a number of eigenfunctions are there, psi 1, psi 2, psi 3 dot dot dot. Similarly, the eigenvalues are small a1, small a2, small a3 dot dot dot. Now, if the system is described by these wave functions, right, this set of psi, then if you try to measure that property, that is capital A, its value, then you will get only the eigenvalues. In a single measurement, you will get one of the eigenvalue, that is small a, not any other value. Okay, so what it writes, generally an operator will have a set of eigenfunctions and eigenvalues, as I told, psi 1, psi 2, psi 3 dot dot dot, and we indicate this by writing like this: a psi n is a n psi n. So a small a n means a1, a2, a3, those are the eigenvalues. Now if you make any measurement, the value you will get is nothing but the eigenvalues. And one prominent example is the Schrodinger equation itself. This is nothing but an eigenvalue eigenfunction equation, right, where h cap is the operator and its corresponding observable is energy. So energy, total energy of the system, it consists of kinetic and potential. So that is the observable, and its corresponding operator, according to postulate 2, there must be an operator, so it is h cap, capital H cap, and it follows some equation like this, which we call eigenvalue eigenfunction equation, and the small e, capital E suffix n is the eigenvalues of energy. Say for example, as you know, for one-dimensional particle in a box problem, this En comes as n square h square by 8m a square. So the postulate 3 says that if you measure the energy of a particle in a box, we shall find one of these energies and no others. So that is postulate 3. Okay, that you will get the value which is eigenvalue. Now, please someone read out this paragraph.
If a system is in a state described by psi n, an eigenfunction of a hat, then a measurement of the observable corresponding to a hat will yield the value an and only an. It is important to realize, however, that the psi n are very special functions, and it is possible that a system will not be in one of these states. Postulate 1 does not say that a system must be in a state described by an eigenfunction. Any suitably well-behaved function is a possible wave function or state function. What then if we measure the energy of a system that is in a state described by psi that is not an eigenfunction of h hat? Indeed, our observed value will be one of the values of En, but which one it will be cannot be predicted with certainty. In fact, if we were to measure the energy of each member of a collection of similarly described systems, or in the state described by psi, then we would observe a distribution of energies. But each member of this distribution will be one of the energies En. This leads to our fourth postulate.
Thank you. So it tells about some problem, that you have a system and you have some functions, well-behaved functions. And now two possibilities are there. Either the function may be an eigenfunction of h hat, or it may not be. Okay. Now, if it is, then one thing. Then if you measure, then always you will get one of the eigenvalues, right? But if you have a function, well-behaved function, which is of course a wave function, but may not be an eigenfunction of h cap, right? Then what? Then still then you may be interested to find the energy. Then what you will get? Because if it's an eigenfunction, then you will get the eigenvalue that you know. But if it's not an eigenfunction of h, then still you are trying to get the energy value, energy measurement. Then what you will get? The answer, it says that it is saying that again you will get like the previous case, you will get the one of the eigenvalue as in postulate 3. But what is the difference? In the second case, that is when the function is not an eigenfunction but a wave function only, in that case of course you will get one of the eigenvalue, but which one, e1 or e2 or e3, that is not certain. You will not get, you cannot predict with certainty. Then what to do? You are not quite sure. Then when you are not quite sure that which one you will get, but of course you will get one of the eigenvalues, but what is the probability of that getting that eigenvalue? Say e1 or e5, you will get one of the, like in a dice, you can get 1, 2, 3 up to 6, but you are not quite sure that in a single experiment what you will get. You are not quite sure. At best you can say that I can say about a probability of getting 3 in a chakka. Okay, if I throw it, if I call it dice. So here the similar case arising, that you are going to get one of the eigenvalues, that 1 থেকে 6 যেমন পুট থেকে 6 হয় ছক্কাতে, সেরকম এখানেও ধর অনেকগুলো eigenvalues আছে, but you are not quite sure which one will happen, will be measured, will be obtained as your result of your measurement. So in that case what we can do? Probability, so probabilistic, or we can say that at best we can talk about some average value, average, gauge, right, on average. So when you are not quite sure, it's not certain, then you can best talk about average. So this leads to our fourth postulate. That means it is going to tell that how you can have an average value of any observable using some function. If the function happens to be eigenfunction, then there is no problem. Even if it is not an eigenfunction of that corresponding operator, still you can use and get the value, but in an average sense. So how you will get the average? That is the fourth postulate. Now you see the fourth postulate. This is fourth postulate. What does it tell? That if the system is in a state described by the wave function psi, and the value of the observable small a is measured once on each of many identically prepared systems, the average value, the average value, also called the expectation value, that means a kind of probability of all those measurements, is given by this. The second version is even simpler. It states that if a system is in a state described by a normalized wave function psi, then the average value of the observable corresponding to operator a hat is given by this. So this is the average sign, a average. Small a average means it is the value, so that's why small a, and this bracket or less than greater than sign means average, and it is given by this integral. It is nothing but all about the fourth postulate. Now what's the difference between these two versions, mathematical forms? You see, the numerator is same, psi star a psi, so here psi star a psi, but here is an extra part, denominator, which is psi star psi, but here no psi star psi is there. So can you tell me?
Is normalized in the second statement.
Right.
So the denominator will give a value of 1.
Right.
So ultimately it becomes the same.
Good. So that's why they are basically the same. Thank you. Now let us go ahead. Let us see. Suppose that psi just happens to be an eigenfunction of a hat. So it follows the eigenfunction eigenvalue equation. Now, but still you apply the average. But you know that actually this psi are eigenfunctions of that operator that you are interested in. But still you are asking that, okay, whether the average formula is very general or not, because in this case the wave function is eigenfunction, so you are supposed to get the particular eigenvalue. You need not go for averaging. But if averaging formula is a very general formula, then it should be able to give you back the eigenvalue as you are supposed to get, because in this case you are starting with an eigenfunction. It is not the requirement of going for averaging at all, because when we need to go for that, when the function is not an eigenfunction. But suppose that you are starting with an eigenfunction and still applying the average formula. So let us see what happens. Psi star a psi, supposing that it is normalized. So psi n star, now a psi n, because its eigenvalue equation is following, so a psi n gives a n psi n small. So a n, though applying averaging for the this case is not just redundant, because anyway you will get that, you will get the one of the eigenvalues a n. Now if you always get a particular value using a particular function, of course the eigenfunction, then what, and suppose that you have measured a number of times, so you should get always a n, right? According to postulate 3, always get a n. So statistically, out of a number of data in a set, and if all are same, then you expect that the standard deviation should be 0, right? Standard deviation should be 0. Now you can evaluate the standard deviation for further clarification. Evaluate the a square average. So you are putting the a hat square, okay, and by same argument it would give you a n square, and a average square. So what is the a average? That is already a n. So a average square is simply a n square, but a square average is again a n square. So what is the variance? Square average minus average square. So you are just taking square average minus average square, and in both the cases they are a n square. So you are getting 0 as expected, because this time you are supposed to get all the values a n, so there should be no standard deviation. This is variance, and square root of this is standard deviation. So if this is 0, then square root of 0 is always 0, so there is no problem. Okay, so this is a further verification, it's not that important, but here is a problem. So by direct calculation of sigma, that is variance in energy, it was sigma in A, but now this is sigma in E, that is E square average minus E average square equal to 0 for a particle in a box, for which psi n x is this. So apparently it looks a big problem that a psi is given to you, and you have to know the operator for particle in a box h cap, and then you have to find E average by applying average formula, then take its square, and in another case you have to take the operator square and then take its average and get the value, and now you differentiate, you are supposed to get 0. This is given as a task, that suppose psi is given like this, between a 0 to a is the length of the box, so psi follows this function and otherwise it is 0. Of course it is not an eigenfunction, because the one particle in box eigenfunctions are square root of 2 by L sine n pi x by L, right? So this is of course not a eigenfunction, but still you can evaluate all the average by using the averaging formula, postulate 4. So you can calculate the average of the system, and the solution is also given. I am not showing it, but I am just giving the remark that after all doing all these things, you will see the value is coming like this. What it is? The average E. That means you have applied the postulate 4 using this psi and using the Hamiltonian for 1D box problem, that is this. Okay, so then if you integrate the whole thing, you will get this value. And note that this value is not one of the energy eigenvalues. Of course, this is not n square h square by 8m L square for any n. This is definitely not any one of the eigenvalues, 1, 2, 3, 4, any one. It's not. because it's an average value, and that average is none of the eigenvalues. It is supposed to be so because you are not taking an eigenfunction. But have you taken an eigenfunction, then definitely after doing this calculation, you might have got it an eigenvalue, any one of the eigenvalue. But here you are not getting, you are getting an average. So note that this value is not one of the energy eigenvalues of a particle in a box. Which one is it closest to? Then probably you will get that actually this eigenvalue is none of the eigenvalue, this average value is none of the eigenvalue, but very close to actually E1, ground state. Very close to, because the function itself is very close to the psi 1. That's why. So after postulate 3 and 4, we are going for postulate 5. And this is something new and something different, because in your UG course, actually the whole lot of problems were time independent problems, right? And here first time we are talking about some time dependence of a function, and of course it is governed by Schrodinger equation, but not the usual one that we have come across, but it is something slightly different. We call it time dependent Schrodinger equation, and that would give you a function which is also time dependent. Okay, so someone please read out on behalf of me this paragraph.
Notice that the wave function in postulate 1 contains time explicitly. This is something that we have not considered yet. Except for this one thing, we have used all the tacitly given postulates in chapter 3, and so all our discussion so far should have been fairly familiar. Now we must discuss the time dependence of wave functions. The time dependence of wave functions is governed by the time dependent Schrodinger equation. We cannot derive the time dependent Schrodinger equation any more than we can derive the time independent Schrodinger equation. It is difficult to try to justify the form of the time dependent Schrodinger equation without using some arguments that are beyond the level of this book, and so we shall simply postulate its form and then show that it is consistent with the time independent Schrodinger equation.
Thank you. So what does it tell? That is actually the basic foundation of taking postulate, that they are not provable, right, as I mentioned. So here also it is stating again that time independent Schrodinger equation H psi equal to E psi, that we took as a postulate, right? Second postulate, that there is an operator for an eigenfunction. Okay, so that was a postulate, and same is true for time dependent part. So neither we can derive in its usual sense, we cannot deduce or derive the Schrodinger equation, either time dependent or time independent. Both of them we have taken as postulates, but it is working fine as far as the experimental result is concerned. It is working fine, so we are accepting it. So this is one thing, and actually time dependent Schrodinger equation is the earlier one, and then we can, on special case, we can show that it is equivalent to time independent Schrodinger equation 2 under some condition. But in the reverse way we have done, we have started with time independent part, and then we are now switching over to time dependent, because it's a bit more complicated, because it naturally it involves one more variable, that is time. Earlier it was only the coordinates x, y, z or r, theta, phi, but now it is along with x, y, z, it is the t also. So this is your postulate 5. The evolution in time of a quantum mechanical system is governed by the time dependent Schrodinger equation. So the left hand side is you see H psi equal to E psi kind of thing, that means time independent part. So left hand side is the same, H psi, but the right hand side involves some time derivative of the wave function psi, along with some multiplication IH bar. So that is postulate number 5. So if you are really interested to see the psi as a function of time, that means time dependent, then we have to solve this equation, right? In earlier case, we have again solved the equation, Schrodinger equation, but time independent. So we got psi, but time independent psi, and that's why we called it stationary state, because in that case psi didn't depend on time. That means with time it does not vary, right? So that's why we call them stationary state. So in other version this is the same, okay, or more or less the same. Postulate 5 is the only one of the postulates presented here that we didn't use in chapter 3. Both the books are saying in the same language, and that we should be new. For most systems that we shall study in this book, H hat doesn't contain time explicitly, and in this case we can apply the method of separation of variables and write. Okay, so one more thing is saying that time is there as a variable coming into the equation, and that would make psi time dependent, but H itself, that Hamiltonian, it may also contain time explicitly or may not. So for convenience, let us suppose that H itself doesn't contain any time, but still then we are interested in time evolution of the whole system. Okay, so H is independent of time to start with, but later on we will see that H itself can also be time dependent, and it is mentioning that about regarding some separation. You see the last line, that we can apply the method of separation of variables and write. Separation of variables, we know this method sometimes very frequently used in mathematics differential equation part. It's a standard way of solving. H hat itself is time independent, then probably we can apply the time separation variable method. Variable means here x is one variable and t is another variable. So psi is a function of both the variables, but can we make it or take it as a product of two separate functions of individually, one is of x and another is of t? That means, can we separate the function as a product of two individual functions, right? A single variable functions. So that is we call the technique of separation of variables. So let us try to go for that. That means we are taking as the product of two functions. So this psi and this psi, you know, it looks different. Okay, so this left hand side psi is a combined function of both the variables, but the right hand side psi is function of x only, and f is another function of t only, and we are supposing that we can take them as a product to give you the overall function. That is the separation of variable technique method. So if you divide both sides, so you can follow it later on. If you just apply this left hand side, this one in this given time dependent equation, then dividing both sides, etc., etc., you can have this equation, and you can follow it later on. So finally you get two separate equations. That means, yes, we could separate the equation into two equations. So initially this, if we integrate this immediately, it would give you, you know, f as a function of t. You can check it later on. I'm not going into the mathematical details. So finally, once you get the ft, then your finally the combined psi is nothing but psi x function only and the t function only. Okay, some imaginary part is also there. So this can be a solution to this Schrodinger equation, time dependent Schrodinger equation, but as a product of two separate functions. Okay. Here something is commented that why we sometimes call classic quantum mechanics as wave mechanics.
Interesting to note that equation 4.74 oscillates harmonically in time and is characteristic of wave motion. Yet the time-dependent Schrodinger equation does not have the same form as a classical wave equation. The Schrodinger equation has a first derivative in time, whereas the classical wave equation, equation 2.1, has a second derivative in time. Nevertheless, this Schrodinger equation does have wave-like solutions, which is one reason why quantum mechanics is sometimes called wave mechanics.
Thank you. So that's all, as you read it out, that both are talking about wave equation oscillating, but they are slightly different as well. In details, the derivative, in terms of derivative, they are different. But anyway, because it is giving you some wave-like equation results or solution, it is called wave mechanics. Fine. One more thing, that okay, so after taking as the product of two separate functions the overall function, this equation, if you just take the square of it, mod square, that means psi square, psi star psi. So if you take the psi n star psi n, so psi n star psi n, okay. So on the right hand side you will get this psi n is different from that psi n I have mentioned. So this psi n, say let us call it small psi, capital psi. They are really so. So psi n star psi n, right? You are taking the product of this into mod of this. Now, if you take the mod of this capital psi, what you will get? Psi n small star, and mod of this quantity is nothing but e to the power plus int by h bar, isn't it? Any complex conjugate, any complex number, its complex conjugate is, if it is a plus ib, then it becomes a minus ib. Simply plus to minus. So when you take the star complex conjugation, then a minus I would become plus I, plus int by h bar, and it is the minus int by h bar. So they cancel out. E to the power 0 is 1. So what we see, that though psi itself is time dependent, but the mod psi square, it is actually the time independent part. It doesn't depend any time on time. So thus the probability density and the averages calculated are independent of time, and psi nx are called stationary state wave functions. As I mentioned earlier, it is all because that your capital H itself is time independent. So if you really start with that, if your system doesn't contain any time explicitly, but you are applying in a time dependent Schrodinger equation, okay, so what you should expect, that okay, the equation is time dependent, but my system is really time independent, so what the result I should get? Time independent. That means even if you use the time dependent equation, finally it gives you something time independent. That's why you get all the average quantity, all the mod psi square, everything to be time independent. Well, we have already covered 5 postulates, right? The first one gives you the wave function. This 6th postulate I am going to talk about is something new. So first we read it out. Wave functions that describe a many electron system must change sign. We call it antisymmetric under the exchange of any two electrons. So altogether, you know, the very wordings of this postulate is quite different. Antisymmetric, something very new concept, exchange of electron, changing sign, many electron system. So all are very new concepts. So hydrogen atom is a single electron system, no? But if you go beyond hydrogen, helium, lithium, etc., then of course there are many electron systems, right? So in that case, how really we have the wave functions and what are their properties? So that is all about postulate 6. Okay. Actually, it is at the heart of what we know as Pauli exclusion principle. You know, the Pauli principle states that a many electron wave functions must change sign if any two electrons are interchanged. So this is taken as a postulate. Okay. Actually, in inorganic chemistry, you have come across this thing, and that's why I'm skipping a few steps. I'm going directly to the representation of an antisymmetric wave function. First of all, antisymmetric means that if you suppose it's a multi-electron, so if you exchange any two electron, say 1 and 2, then after changing or exchanging, you will get the wave function, and before change you have done another wave function. So they must be related, that one is the minus of the other. That means the sign itself changes. It must be, that is the postulate, that it has to be like that, that if you exchange two electrons, then the wave function must change its sign, and that property itself we are calling that it is antisymmetry. That means, in other words, we say that our wave function is an antisymmetric wave function with reference to exchange of two electrons. Now, how we can mathematically represent that? Suppose we have n electron wave function. So psi is a function, and how many electrons? 1, 2, 3 up to n. Now the right hand side, this is actually a very compact notation of an antisymmetric wave function. Antisymmetric in the sense that if you exchange two electrons, the sign would be changed. Okay. Well, what it looks like? First of all, this 1 by root n is a normalization constant like kind of thing. So don't bother much about that. Now, this phi 1, alpha 1, what they are? Phi 1 and alpha. So bracket 1 is within bracket 1, 2, etc. They are the electrons level. So electron 1 is here, electron 2 is here, electron 3 is, electron n is here. That is a separate thing. But what the phi 1s are? Phi 2 are, phi 1, phi 2, then phi 3, then phi m, etc. They are the single electron atomic orbitals, like 1s, 2s. Okay. So they are the single electron atomic orbitals, phi. And what are alpha? Alpha or beta? They are the spin part of the orbital. Spin part, special part and spin part. There are two parts, phi and alpha or beta. Now you are arranging or accommodating the electrons. It's a matrix, I mean determinant. So the first row you observe that phi 1, then phi 2, then phi 3, then phi m. So they are coming in pair. And why pair? Because phi 1, but one is alpha, one is beta. Then phi 2, one is alpha, one is beta. Then phi 3, phi 4, up to phi m, one is alpha, another is beta. So that means m is actually n by 2. If there are 8 electrons, then actually you need 4 special orbital, and each special connected to 2 spin. So 4 into 2, that gives you 8. No problem. So that is the first row looks or reads like that. That it corresponds to the first electron, but the wave functions are like phi 1, phi 2, phi 3, and so on. And the same thing happens that phi 1, again phi 1, alpha beta, phi 2, alpha beta, same thing, but only difference is that this time the electron is second electron, 2, 2, 2, 2, 2, 2, 2. Similarly, the next one is again phi 1, 3, alpha 3, right? Phi 1, 3, beta 3, phi 2, 3, alpha 3, phi 2, 3, beta 3, and dot dot dot. And the last line, phi 1 n, alpha n, then phi 1 n, beta n, then again phi 2 n, alpha n, phi 2 n, beta n, and so on. Finally, phi m n, alpha n, phi m n, beta n. So this is the, it would be more easier to see and understand if I go for a simpler example, 2 by 2, but I am trying to explain it in general. Now, why this special type of representation of a wave function? It looks like a determinant, and it is. It's not no way looking like a wave function, but actually it is. How? First of all, let us understand that how this is antisymmetric. Now you see, as a determinant property, if you exchange two rows, any two row, what would be the value result? Do you know? If you take any determinant and you exchange the two rows, what will be the resultant determinant?
Negative.
Exactly. It would be negative of the given one. So exactly that is the property we are using here. If you exchange two rows, that means you are putting all twos here and all ones here. That means you are exchanging electron 1 and electron 2. Right? So exchange of two electrons here means exchange of two rows, and the result is negative, as we suppose in our postulate. So that's why this presentation. And one more thing, if two rows are exactly identical, then what will be the result? If two rows
Zero.
are 0, that means the wave function doesn't exist. Okay. So that's clear. You know that much of mathematics, that from determinants property you can easily say that if two rows are identical, then the result is 0. That physically means that there is no left hand side which is 0. That means there is no wave function at all. And now practically what does it mean? Two rows are identical. That means here is 1 1 1 1 1, here is also 1 1 1 1 1, right? That means here to note that interchange of two rows change the sign, okay, and it is 0 if two rows are identical. That is exactly what Pauli exclusion principle states you, right? That is exactly Pauli exclusion principle states that two rows are identical, actually equivalent to say that two electrons having same set of quantum numbers, 4 quantum numbers. That would be clear from the example later on. So the concept, this determinant has a name. It is called Slater determinant after the scientist Slater. So Slater determinants provide a convenient way to make many electron wave functions antisymmetric in the orbital approximation. Okay, now let us see quickly a smaller example. Say for example helium. So for ground state helium, okay, ground state helium. So it is going to be 2 by 2 problem because there are two electrons, 1 and 2, and the spatial orbital I am taking. So how many? Half of this 2 electrons. So we need only one spatial orbital and 2 spin, half an alpha and beta. So 1s1 is enough as spatial orbital. So what will be the determinant? 1s1 alpha 1, 1s1 beta 1, and the next one is 1s2 alpha 2, 1s2 beta 2. The first row for electron 1, the second row for electron 2. Okay. Now if we expand the determinant, then cross multiply and then minus this cross multiplication, so it would look like this. Okay. Now you see 1s1 alpha 1, 1s2 beta 2, or here 1s1 beta 1, 1s2 alpha 2. So 1s1 1s2 and 1s1 1s2. So we can take common actually. So 1s1 1s2 you take outside the bracket. So remaining is alpha 1 beta 2 minus beta 1 alpha 2. Alpha 1 beta 2 minus beta 1 alpha 2. Okay. So this is the wave function it proposes, keeping in mind that it is supposed to be antisymmetric. When? Because of exchange of two electrons. Now you think, you try to exchange electron 1 and 2. That means wherever you see 1 you put 2, and wherever you see 2 you put 1. Then you see the result. What would happen? This 1s1 and 1s2 remains the same, because if you put 2 here and 1 here, it remains the same. Basically it is the product of 1s1 1s2. So after exchanging it will remain the same. But what happens here? It is alpha 1 beta 2 beta 1 alpha 2. Now after exchange it will be alpha 2 beta 1 and beta 2 alpha 1, and that is exactly the negative of the starting one. You can check it on your script. If you have pen and paper with you, you can immediately check that if I exchange 1 and 2 between these 2 alpha 1 beta 2 and beta 1 alpha 2, then the resultant is nothing but negative of this starting one. That means the whole thing would be negative of the starting one. So you can, it easily demonstrates that if you express in the form of Slater determinant in this way, then you are sure that you are going to get an antisymmetric wave function, antisymmetric in the sense with reference to exchange of any two electrons. So here the last line you see, to note that for helium N, L, Ml for two electrons are same, but not Ms. So two electrons, N is 1, both are in 1s orbital. L is 0 because both are s orbital, right? So N, L are same. Ml is 0 only for L equal to 0. So Ml is only 0. So N, L, Ml all are same, but alpha and beta they are different. 1, 2, 2, 1, right? So, but if you take the two rows identical, then you will see both the electrons having all 4 quantum numbers to be exactly the same. But that is not against Pauli exclusion principle, and that we get also from here. So that is all about the postulate 6, something new. And one more thing as a task. Suppose this is the, as I mentioned, alpha and beta, what do they really mean? It is something like this, that it is talking about the spin, clockwise or anti-clockwise. So one is taken, suppose this is alpha, up arrow, and down arrow is beta. It is clockwise and it is anti-clockwise. This is anti-clockwise, this is clockwise. Okay. So keeping it in mind, suppose you have been given four possibilities, that helium excited state. Okay, so energetically one is lower and another is higher. That means as special atomic orbital you take 1s and 2s. Okay, special orbital. And what about the spin? Four occasions, up down, down down, and down up. So four possibility. Now for each of them you can take as a problem that if this is, suppose A, the first one, if this is your situation, that 1s 1 and 2s another electron, the first electron is half spin up and the second electron is down spin. So what would be the Slater determinant? What it would look like? The solution is this. You see now next B, C, D you will give me. You see the special, as I mentioned, that 1s and 2s, because the ground state and excited state. Energetically there are two different states. So 1s and it is half spin up, so alpha, and the second one is 2s beta. Okay, so this is for one electron. The second electron you write again by according to the rule, that again you write 1s 2s alpha beta, 1s 2s alpha beta, but this is not 1 1 1 1 and this is here 2 2 2 2. So this is your answer to this question, that give the Slater determinant form of antisymmetric wave function when the system description is like this. So now would you try please to answer the second part, that is
First row, 1s1 alpha 1, 2s1 alpha 1,
right, and then
and second one same হবে, মানে 1s2 alpha 2, 2s2 alpha 2.
you must check. Now you check whether you are right or not.
S1 alpha 1, 2s1 alpha 1. Yes, sir.
Yes, you are right. Thank you. So you have got my point. So any other one, please give me the answer for C.
1s1 beta 1, 2s1 beta 1.
Right.
First row, second row te 1s2 beta 2, 2s2 beta 2.
Good. So you check. So similarly you get the fourth one also. Okay. Now if you expand, you can check it later on. If you expand and you verify whether these functions are antisymmetric with respect to exchange or not. Okay. So that is given as a task to you. Now one last part, that suppose we are considering now 3 electrons. Helium is 2, hydrogen is 1, but now suppose lithium, there are 3 electrons, 1 2 3. Then of course third electron, where should I put it? Supposing that let me put it in the 1s again. So 1s 1s 1s. So how I can put it? 1s alpha, 1s beta, and then 1s alpha. Let me by force, brute force, let me think of that. Now 2 2 2, now 3 3 3. But what would be the problem? Because this column, these two are exactly the same. You see the problem where it is, where the third electron can have either alpha or beta. I am put 1s, one is alpha, another beta. But the third electron I would like to put it again in 1s. So fine, 1s. But what about the spin part? It would be either alpha or beta. So let it be alpha. Okay. Now, however, the first and third columns in the determinant are identical. So if you brute force, if you jor kore gayet jor jodi amra korteo chai, what would be the result? The first column and the last column will be identical, and that means again by determinant property it would be 0. That means the whole thing would be 0. That means therefore the third electron must go into the next higher energy orbital with n equal to 2. So you cannot take the third column as such, because according to this Slater determinant form it would not exist. that means there would be no wave function existing. So you have only one option left, that the third electron you must push it to some higher spatial orbital. Of course, spin you can take either alpha or beta, no problem. That would make it not identical, and that is actually equivalent to say that this example shows that the Pauli exclusion principle requires that each orbital have a maximum occupancy of 2 electrons, right? So Pauli exclusion principle we use class 9 or 10 maybe, right, or maybe 11, 12. But where from it comes really, it is to some extent quantum mechanics, of course, and to some extent group theory and symmetry, because this anti-symmetry concept is typical of group theoretical subject. No? And you are in SEM 1, probably in SEM 2 you have group theory courses, and if everything goes okay, then I will be the same person who will be taking that symmetry course, group theory.